Okay, welcome. There were 4 problems for homework on the finite projective plane. 21, 22, 28, and 29. 21 says, so this was your time to finally do one of these finite projective plane proofs on your own. So let's go. So here's 21. It says, let L1 and L2 be 2 distinct lines in a finite projective plane. So we have L1 not equal to L2. And the theorem says, prove that there's a point that is on neither L1 nor L2. So show there is a point that's not on L1 and not on L2. Okay, so I know I said in the directions to not use anything but the axioms, and actually that is possible. If you read what Gossett does in the back of the book, it's kind of confusing because he skips a lot of steps, I think, in my opinion. Then you can see how this can be proved directly from the axioms. And actually in a Wednesday afternoon period 7 Zoom call, we did this whole proof straight from the axioms, but it was annoying. So I changed my mind. I'm going to change the homework as well, because I just think that we don't need to use, we can use some of our previously proved theorems. In particular, I would like to, well, if you use, well, I'll push ahead. So I'm going to use lemma 8.3, and lemma 8.3 says that there are greater than or equal to 3 points on each line. So every line has at least 3 points on it. And I think this was our most challenging and most abstract proof from this entire mini unit. It's the proof that I didn't know how to do, that Gossetts Proof, I think, is incomprehensible and wrong, and Daniel Zhu showed me how to do it 2 years ago. So see that video for the proof of this, but we put so much effort into proving that there are greater than or equal to 3 points on each line, that I think we should just use this theorem. And if you use this theorem, suddenly things become a lot easier, so that's good too. Okay, let's go, but still kind of hard. So here's how you do this this problem. All right. Well, and note that we're going to do it like analytically, which is to say, all of the argument is going to be written on the paper, and the picture is just going to guide our reasoning. All right. Well, I have these 2 points, L1 and I have these 2 lines, L1 and L2. I want to show that there's a point that's not on either of them. Okay. Well, let me draw L1 and L2. So let that be L1 and let this be L2. And of course, we know that these 2 lines intersect at some point P, and that's by FPP2. So note that we need to know that they're different. So by FPP2, there is FPP2 says every 2 distinct lines intersect. So at exactly 1 point. So by FPP2, let the intersection of L1 and L2 be this point P. Okay, so what do I know about this point P? I know that P is on L1, and I know that P is on L2. Okay, and I'm going to put a kind of box around every sort of important fact as I establish it. Okay, great. What now? Well, there have to be other points on L1 and L2. And actually that's sort of what's nice about this. Just thinking for a second about what I want to do here. Yeah. Okay. By virtue of this lemma 8.3, I can now just like put more points on all of these these lines. And so I'll put another point, let's call it P1 on L1, and I'll put another point, P2 on L2. Let me just do this. Okay, and yeah, so I'll write that. So by lemma 8.3, so now I don't need to, I don't need to engage anymore in the extremely low level reference to FPP3 anymore, which is very kind of abstract. Instead, I can just go right for this. By lemma 8.3, there are other, in fact, there's at least 3. There are other points on L1 and L2. So take some other point, because this theorem guarantees that there exist at least 3, take a point P1 on L1, specifically P1 being not P. So P1 is not P, so take a different point. And also take a point P2 on L2 with P2 not equal to P either. Okay. Well, this is great because, so I have this, and alright, because I'm kind of disciplined and experienced with these proofs, I know that, okay, while the picture is very nice, I need to prove every single tiny little stupid thing because that's what makes it an actual proof from the axioms. In particular, my eyes tell me that P1 is of course not on L2 and that P2 is not on L1, but let's just prove that really fast. And okay, here's what we can say. If P1 were on L2, so this is a little kind of mini proof by contradiction here, well then what would we have? We would have, the problem with that is that's just what L2 is, man. So there are different ways to phrase this, but maybe the simplest way is to just list all 4 facts. If P1 were on L2, then I would have P1 on L2, but also P on L2, but also P1 on L1, and also P on L1. And we have by FPP2, what FPP2 says that 2 distinct lines meet at exactly 1 point. But this has 2 distinct lines, L1 and L2, meeting at 2 distinct points, P and P1. P and P1 are different, L1 and L2 are different, so this is a contradiction with FPP2. And so, conclusion, P1 is not on L2. Put a box around that. Okay, we have one more opportunity to engage in this kind of reasoning. Similarly, if P2 were on L1, then what would we have? Well, we would have both P2. There maybe are other ways to write this, but we would have both P2 on L1, but then of course also P2 is on L2. And that means, and since P is on L1 and P is on L2, then once again this is a contradiction with FPP2. The more casual way of doing this is to say, look, of course P2 can't be on L1, because if P2 were on L1, then since P1 is on L1, then the line through P1, P2, since I misspoke there. So if P2 were on L1, then if P2 were on L1, then P and P2 would both be on L1. But L2 is the line through P and P2. So L1 can't be the line through P and P2 because L1 and L2 are different. But I don't know, maybe this way where you write everything out in tiny little steps, maybe this is more clear. What we have just established now is that P2 is not on L1. Okay, so even using this lemma, this is shorter than the proof that's in Gossett and the proof we did in the Zoom, but this is still pretty hard. Okay, what next? Well, I shall now invoke FPP2 to say that there's some line here. So here, there is this new line. Let's call it M. So yeah, I have these 2 points, P1 and P2. Oh no, there's one more thing left. Note that I haven't actually shown that P1 and P2 are different yet, but I'm now prepared to do so. And the fact is that they have different properties, right? P1 is on L1, but we've just shown that P1 is not on L2, and so we conclude that P1 is not P2. And having taken the time to establish this, I may now, in Incompetence, invoke FPP1. So by FPP1, we have a line M which goes through P1 and P2, because that's what FPP1 says. There's a line through every 2 distinct points. So there, P1 is on some line M, and P2 is also on some line M. Okay, great. What now? Well, now, although this seems silly, I think I should immediately show that M is not either of L1 or L2. And the logic is kind of the same, right? What is the problem? If P1 were on, and now I'll introduce a sort of different notation, maybe you prefer it. If P1 were on, if, what was I trying to say? That M is different from L1 and L2. Actually, the thing I want to do first is show that P is not on M. I think that's the simplest thing to do first. So if P were, no, wait. Lost my train of thought. 1 second. Oh, yeah, the simplest way to show that M is not equal to L1 or L2 is to, okay, so since P1 is on M, by construction, M is aligned through P1, but P1 is not on L2, we established that, then I know that M is not L2. So this is really just a new line, your eyes don't deceive you. If since P2 is on M, again that's the definition of M, and P2 is not on L1, we showed that. That means that M and L have different properties with respect to instance with P2, so M is not L1. Okay, so this is now like a new line, this line M, and now I will show that P is not on M. And if P were on M, that would be bad, because if P were on M, well then the line through M would go through both P and P1. But we already have a line through P and P1, L1, and M is not L1. So I changed my mind. I'm not going to do new notation. I'll stick with the old notation. If P were on M, then what we have is we have P on M, but we also have P1 on M by the definition of M. But of course, P is also on L1, and P is also on P1 is also on L1, and the only way for this to be true is if M equals L1. This is a slight variant of what I wrote down there, but that's a contradiction because we've already established that M and L1 are different. Okay, so P is in fact not on M. Okay, so I got this line M now, and it goes through P1 and P2, and it doesn't go through P. And now I once again invoke lemma 8.3 to say that there's some other point on this line M. Call it Q. Okay, so yeah, we continue. So by lemma 8.3 again, there's some point Q on M where Q is not P1 and Q is not P2. Okay, that's just the by construction, that's what Q is. It's a third point on this new line M through P1 and P2. And what was I trying to do again? Oh, I'm trying to show that there is a point that's not on L1 and L2. Well, there it is. I claim that Q cannot be on L1 or L2, thus proving the theorem. Why not? And well, now I just finish it off. If Q, I think that's all I need to do, right? Yeah. If Q were, let's see, do I need to, I don't even think so. I don't think I even need to do anything else. Well, let's find out. So if Q were on, there's a point now I want to, so if Q were on L1, say, what's wrong with that? Well, then L1, yeah, so then you'd have Q on L1, Q on M, but also L1 and M share P1. So P1 is on L1 and P1 is on M. And again, that would conclude by FPP2, since every two lines intersect at two distinct points, and these are in fact two distinct points, then these two lines would have to be the same, but they're not the same, is another way of putting it. Okay, so this is FPP2. Or alternatively, you can say they are distinct lines and they are distinct points, so it's just an immediate contradiction with FPP2. Either way, so that was my one of my key facts, and then I think I'm just done, right? Analogously, if Q were on L2, then you would have you'd have Q on L2, but also P2 is on L2. And Q is of course on M, and also P2 is on M. M was defined to go through P2. And so now, according to FPP2, since every two lines distinct lines can intersect at well, since every two yeah. I guess it's really not, I guess it is maybe kind of more clear to say from this that we just have a contradiction with FPP2. Maybe that's more clear. Because we've already shown that these two lines, M and L2, are distinct, and we know that these points Q and P2 are distinct, and so we have two distinct lines intersecting at two distinct points. I think that's a clearer way of concluding the argument. Oh, sorry, this was not what I meant to put a box in, because this was an if. So I said if Q was on L1, then all this stuff leads to a contradiction with FPP2. And once again, if Q were on L2, this leads to a contradiction with FPP2. And so it means that Q is in fact not on L1, and Q is in fact not on L2. And actually that was the goal of the theorem, to show that there was some point which was not on either of those two lines. And we kind of constructed it. And what is this point Q that's not on L1 or L2? It's ultimately, it's the third point on the line through two other points on those lines besides the point of intersection. That's like the 30-second explanation. Okay, so I hope that was a pretty good explanation and extremely kind of slow and clear, and sort of modeling how you would kind of do these things. All right, 22 is just exactly the dual of this, so I'm just not going to do it. You figure it out. If you want to do it the way I have done it, then you are going to need to use the dual theorem of lemma 8.3. Which is, since in a finite projective plane there are at least 3 points on any given line, it's also true that any given point lies on at least 3 lines, or that there are at least 3 lines that go through any given point. So if you use that dual, then you can prove 22 in exactly analogous way. Or you can do it the more hardcore way, where you don't use that lemma and you just take it straight from the axioms. That's more work. And I believe that's what I did in the video. If you go to the beginning of the video 1 of the lecture called Day 5, you can watch me going over number 22. And I think I do it the long way. Alright, good. I'm going to call that done. The more exciting thing now are these 2 conversions. And I didn't really prepare this or anything, but I think I know how to do this. So let's go. 1, 2, 3, 4. 2, 1, 4, 3. 3, 4, 1, 2. And 4, 3, 2, 1. And 1, 3, 4, 2, 4, 2, 1, 3, 2, 4, 3, 1, and 3, 1, 2, 4. Okay, and great. Those are both Latin squares, of course, and they are, we're just taking Gossett's word for it, they are mutually orthogonal. Is that clear? It's not clear to me, but you can just do a quick spot check of this fact. The 1s all lie along that diagonal, those are all different. The 2s go ch-ch-ch-ch, so 3, 4, 1, 2, all different. The 3s are ch-ch-ch-ch, and those are all different. And the 4s are all different, so no ordered pairs are repeating. But now, a harder thing to do, says Gossett, just as a little, let's see if you can do it, and let's see if I can do it. He says, produce a third mutually orthogonal Latin square, which is produce a third Latin square, which is mutually orthogonal. So orthogonal to each of these. All right, let's see if I can do this. I think I have it written down somewhere, but anyway, I'm doing number 28. Okay. What goes here? Well, can't be a 1, of course. What else could it be? It could be a 2, it could be a 2, a 3, or a 4. But by comparing it with this Latin square, let's see, the ordered pair 1, 1, 3, 4, 4, 2, and 2, 3 have already been taken. So this is a 4. So there's already a 4, 2 ordered pair with respect to this Latin square. So if there's already a 4, 2 ordered pair, and this is about to be a 4, then this can't be a 2. So this can't be a 2 or a 1, so it could be a 3 or a 4 seemingly. But can it really be a 3 or a 4? Because I need to make this square mutually orthogonal to this square, orthogonal to this square as well. So this would be a 3 or a 4. Well, now comparing this first row and this first row, we see that I'm about to make a 2 something, but there's already a 2, 4, so there can't be a 2, 4. So this has to be a 3. All right, if you follow that, I ruled out a 2 because I need to, because I'm filling in the column underneath the 1. I ruled out, wait, sorry. I ruled out 1 because I'm in that column. I ruled out 2 because if that were a 2, then I would have a 4, 2 ordered pair, but I already have a 4, 2 ordered pair. And I ruled out a 4 because I would have a 2, 4 ordered pair, and I already have a 2, 4 ordered pair. I think I'm doing this right. Okay, what now? I think it's best to go down this column, although I'm not really sure. What goes here? Well, it has to be either a 2 or a 4, of course. Could it be a 2? Well, no. Because if this were a 2, then I would have 3, 2 ordered pair, but I already have a 3, 2 ordered pair. So this can't be a 2. So it must be a 4, and then that must be a 2. Okay, let's keep on going. What could go here? Seemingly it could be a 1 or a 2, but suppose it were a 1, that would be fine, seemingly. Could it be a 2? If it were a 2, I don't see any problem with that. Oh wait, sorry, let me go back again. Oh man. Sorry, this could be a 2 or a 3. If it were sorry, this could be a 1 or a 2. If it were a 1, then I'll be about to write a 2-1 ordered pair, which I don't see any problem with. But if this were a 1, I would about to be writing a 1-1 ordered pair, but there's already a 1-1 ordered pair. So to enforce orthogonality with the first Latin square, this can't be a 1. So this has to be therefore a 2. Okay, at some point this has got to start getting a lot easier. Maybe now. No, still not. Oh my god. Well, I'll just keep going. What can go here? This could be seemingly a 1 or a 4. But if it were a 1, then I would have a 1-1 ordered pair, but I already have a 1-1 ordered pair, so this can't be a 1. This has got to be a 4, so this has got to be a 1. And now, please tell me I'm done. Let's see, yeah, that has to be a 2 to make it a Latin square. This has to be a 4. So, man, I'm still not done, seemingly. Okay, let's just keep on going. What goes here? This could be a 1 or a 3. If it were a 1, then I would have a 4-1 ordered pair, but... Hold on. If it were a 3, then I would have a 4-3 ordered pair, but I already have a 4-3 ordered pair, so this can't be a 3. So this has got to be a 1, so this has got to be a 3, so this has got to be a 3, so this has got to be a 1. Alright, if I were you, I thought that was like hard. I would now double check this. I am double checking with some work I did a million years ago. Alright, so I thought that was quite hard. But actually that might be the easiest way. This might be the most human thing to be able to have in our power, is this ability to write these mutually orthogonal Latin squares. And so, okay, I haven't actually proved that I've done this correctly, but I'm pretty damn sure it's right. What you should now do is check that these two are, well, we already did with these. And okay, I'm not going to waste camera time doing this right now, but you can, once again, go through, focus your eyes on where the ones are, and make sure that in those 4 spots, the 4 different numbers are represented. And if you do that, you'll see, yeah, 1, 4, 2, 3, and you can just do that for every number and show that these two are orthogonal, and then that these two are orthogonal as well. I'm just checking now because I can, and it doesn't take too long. Now the 2's, so I've just brute force confirmed this. 3, 2, 4, 1, and the 3's. I've never actually done this before, but you can't see what's going on in my brain, but I'm just focusing my attention on these 4 3's, and I'm just looking and saying 4, 1, 3, 2, and the 4 4's, 3, 1, 2, 4. So, okay, I have now brute force checked that I have 3 mutually orthogonal Latin squares. Alright, what am I supposed to be doing again? I am supposed to be constructing, from these 3 mutually orthogonal Latin squares, a set of lines. And, okay, here is how you do this. The first thing you do is to recognize that, okay, so what is orthogonality? 2 Latin squares are orthogonal when, if you superimpose them and create ordered pairs, the ordered pairs don't repeat. Well, now I'm going to blow your mind, or not, if you watch the video, then you already got this message clearly, that really there are 2 more squares floating out there. The square 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and the square 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. What are these squares? They are squares. They are not Latin squares, of course, but they are squares. And in fact, if you, we can now consider these two squares to be also orthogonal to each of these Latin squares. In fact, orthogonality of any square, of any Latin square, with this square, with where the columns are 1s, 2s, 3s, and 4s, is in fact just the defining property of a Latin square. Because what do we mean? What does it mean to say that these two are orthogonal? It means that no ordered pair repeats. And for no ordered pair to repeat, then since let's take the ordered pairs as going like this first, then that one. So since these are all 1s, then that's just saying that 1, 2, 3, and 4 all have to be different. In other words, the very definition of the Latin square as having the column property that every number must appear exactly once in each column is equivalent to saying that that square is orthogonal to this square. That's kind of brilliant, I think. And I failed to say something this clear in this afternoon's 9th period Zoom call. That's really what's going on here. This property of orthogonality is best thought of as applying not just to Latin squares, but in fact can define Latin squares. There are these two. Okay, I'll keep going. These two squares. What does it mean for these two squares to be orthogonal? Well, since if I think of the left member of the ordered pairs being this one and the right member this one, well, I have 1, 1, 1, 1, so these numbers better all be different. And these are all 2s, so these numbers better all be different. In other words, by enforcing that these two are orthogonal, I satisfy the row property. In other words, you may simply define a Latin square as a square which is orthogonal to each of these two squares. That's just what it means to be a Latin square. And so, though I have these 3 Latin squares, I have these sort of other 2 squares floating around in the background. And now we're just kind of done. Because these numbers are just the lines. And that's it. So, you take your 16 points, and, oh wait, I thought a little bit more about how I was going to do this on the video. If I had a lot of board space, I would do something, but as I don't, let's see. Well, okay, yeah, I think this is the better idea. Let's label these points 1 through 16, but let's not actually write the numbers 1 through 16. Let's just keep that in our brains. Maybe this is a good idea. So I'm now going to write 5 of these. I'm just going to kind of repeat it, I guess. I'm going to leave some work for you to do here because, you know, come on. Or maybe, can't decide what to do. Maybe I should write smaller and try to squeeze another one in. So 1, 2, yeah, that's what I'll do. If I make one picture, in some ways that's better, but I don't know if it will be clear what the hell is going on. And let me make